Alright, let's see. Looks like we're ready to roll. Looks like the audio is pretty good. Let's go for it. PowerPoint ready to go. Go. Alright, students, as I promised, here's the chain rule. So here's a list of things we're going to talk about, including the general power rule, which I've sort of mentioned before. And I mentioned about the derivatives of functions using the chain rule. So let's get to it. The chain rule. I couldn't avoid this. We had to do the chain in there. 2 chains to boot. Okay. It's a powerful rule. In fact, what I would suggest is every time you go to differentiate, whether you have to use the chain rule or not, think chain rule. Now, the chain rule is mostly for composite functions. That means functions inside of functions, but it adds versatility to the rules, as it says. One way of looking at the chain rule is the first one down here. And just so I've got things rolling here, let's get this pen rolling. Now, this is a really nice way of looking at it, but I'm not sure how easy that is to use. This y represents the big function. The u represents the inside function. Outside function, inside function. A short way of describing it is you're taking the derivative of a function that has a function inside it. Or you might write it like this: d dx, f, and g is the inside function. And the derivative of that combination or composite function is the derivative of the outside function and then times the derivative of the inside function. That's what this represents. This is another way of describing the same thing. And although the du's look like they cancel, that's not exactly true, but effectively, yes, it is true. So, that way of describing it makes things pretty easy if you can figure out what dy du and du dx represent. Chain rule. So first of all, you figure out which is the inside function, which is the outside function. This u that we have right here is the inside function. Notice that we're going to take the derivative of that and we're not going to touch it. We're going to leave g of x exactly the way it is. Here we're calling it u to just make it simple. We're going to take the derivative of the outside function. In fact, what you might want to do is rewrite this one. Here's our original function, with one function inside the other. Just to make it a little bit simpler, let u be the inside function. to keep from getting confused. So another way of writing y, the one we're interested in, is we've got f of u. And to take the derivative of that, we're going to take u, and we're going to find dy du. We're going to temporarily sort of ignore the g of x and just get dy du. Once we've got the dy du, then we're going to take the derivative of this one. We'll have du dx, which is the derivative of g of x. We'll multiply this by du dx, and that'll give us what we wanted to begin with as dy dx. So how do I use that du dx and all that stuff? Okay, first of all, I've got an inside function and an outside function. If I were a calculator and I was doing these things as functions, the outside function says cubing. The inside function says square and add 1. So I'm going to call this u temporarily. Let u represent the x squared plus 1. The nice thing about this is it makes things simpler. So if that's what u is, then this y right here is going to be just u cubed. Well, gee, that makes it seem simple. Take the derivative of this one, call it dy du, because u is our u is our variable, so we're going to take dy du. What is it? Easy. Bring the 3 out front. Don't worry about the inside function. We're just calling it u. That u now has an exponent of 2, and there's my function. Now this isn't x, so what I need to do by the chain rule is take du dx. Well, what's du dx? Well, u is x squared plus 1. So what's du dx? Well, that's simple to do too. X squared, the derivative of that is 2x. The derivative of 1 is 0. There's du dx. So my y prime dy dx is dy du times du dx. Dy du was 3u squared, and du dx over here was 2x. Oops, prime. So what's dy dx? Well, let's take this value for u and put it back where it belongs. Instead of u represents x squared plus 1. So we've taken this and we'll put the x squared plus 1 back in where it needed to be. That's times the derivative of the inside function, and we have a little bit of cleanup at the end here. The dy dx that we really wanted is, we're not going to move the 2x out front, 6x times x squared plus 1 squared. Done. That's it. So what you do is, first of all, find the inside function. Let u, or whatever letter you like, we'll stick with u. Let u represent the inside function. That makes it easier to write the y. Write the y using that u that you just created. Take the derivative of both of them, put it all together. You've got your answer. No messy here. And there's our answer. The general power rule. Notice it's a special case of the chain rule. You've got a function inside, so you're going to bring that n outside, leave this alone, reduce this n by 1, and then you'll take the derivative of u to the x. So here's a description of what I just said. The u that was out in the exponent row, you bring it out front. And there's the n brought out front. The n now becomes n minus 1. And because this isn't just an x, we'll take the derivative of that with respect to x. Once you've done that, a lot of times you'll need to simplify a bit, and you've got your answer. Here's another way of saying the same thing. Bring that n out front, and there's our n. Reduce the exponent by 1, that's the n minus 1, and then take the derivative of that inside function, u prime. Another way of looking at the same thing. Remember what I said earlier. Every time you differentiate, think power rule first. Think chain rule. Use that chain rule with the power rule, and you can do wonders with things that are much more complicated than you could a week ago. Here's an example. Now here we are back with the tangent line thing again, but remember, if we want to find the equation for the tangent line, we need to find the slope. And it tells us where we're going to find the tangent for. So we're going to have to find the slope. We also need to get a point. Once you've got those two, here's your point-slope form one more time. You put the point in for x sub 1 and y sub 1. You put the slope that you get from differentiating. You put that here, clean up, and you've got your answer. Okay, so that's the easy part. You've done that already. Come on, get with it. I mean, talking about me. Now, what do we have over here? Y equals this. And this is a complicated function. It's a function inside a function. We've got the cube root of something. And so first, let's get things a little bit simpler. Let u be the part that's inside. X squared plus 4 is the part that's inside. Well, notice that you've got a cube root and a square. We can combine those two. That's a power of 2, root of 3. So I can write this whole thing as u to the 2/3 power. All of a sudden, we've got something that's pretty simple for us to work with. So we'll differentiate. So dy du, remember we don't have an x right now, we'll come back to that, equals, bring the 2/3 out front, the u becomes a negative 1/3 because we subtract 1 from the 2/3, and du dx, because we differentiated u with respect to x. So what do we have? Oops, don't need that. So what's dy du? Yes, I do need that du dx. Okay, so what have I got? Well, while I've got this, I might as well work with that. Take the derivative of that. Du dx, what's that? Well, that's easy too. 2x plus 0. I'll bring that over here where I've got dy du. That's 2/3 u to the negative 1/3 power du dx. Hey, I just found du dx. 2x. How about the u? Okay. To get dy dx, we'll take that 2/3. The u is really x squared plus 4, negative 1/3, and 2x out here. So what's dy dx? Dy dx, I can bring that 2/3 out front. I'll have 4/3 x of x squared plus 4 to the negative 1/3 power. Okay, next, we've got the slope at any particular point at all. What we want, though, is we want dy dx at a particular place. We want that slope where x equals a 2. So I'll just put 2 in where the x is. I've got 4/3. I'm just using this right here. 2 is the x we're using. That's the point. Inside, I've got x squared plus 4. X is 2. So 2 squared plus 4. And to the negative 1/3 power. What's that give me? It gives me dy dx. And that's going to be our slope. What do I have? I've got 4/3. Since we've got fractions, I'm going to write everything as a fraction. And this will be 2/1. And here I've got 4 plus 4, that's 8. I'll write that as 8/1. And that 8/1 is the -1/3 power. So I'm going to bring that up here so I get a little bit more room. So my slope is 4/3 times 2 would be 8/3. That's the first two factors. Now I've got 8/1 times -1/3. The first thing I'm going to do is, it's a -1/3, that means I invert the 8/1. So I've got 1/8 to the 1/3 power, because that negative exponent means reciprocal. So what's my slope? My slope is 8/3. Now I need to take the cube root of the top. The cube root of 1 is 1. The cube root of 8 is 2. And my slope, I can reduce that by 8/6, or 4/3. There's my slope. Now I need the point. How do I get the point? Well, this function that I'm using, of course, as usual, tells me how I put the x's and y's together into ordered pairs. So I've got an x of 2, that's the one I'm interested in. What's the y value that goes along with that? Well, my function says the cube root of x squared plus 4 squared. And I'll put a 2 in where the x is. Y equals cube root of x squared is 2 squared. So that'll be 4. 4 plus 4. Let's put all this down. 8 squared. That's 2 squared. That's 4 plus 4 is 8. And we're still squaring it. What do we get for y? Okay. We got to square the 8 first. So I want the cube root of 64. A little bit of calculator work perhaps, or maybe not. The cube root of 64. 4 cubed is 64. So there's our y value. What does that give us? We just found that one of those points on that curve is the point 2, 4. That's a point. Where am I? 2, 4 is one of those points on that curve. Now I've got the point 2, 4, and I've got the slope 4/3. I'll put them together. Y minus 4 equals 4/3. X minus 2. There's my equation before the cleanup. Excuse me. So y minus 4 equals 4/3 x minus 8/3. Y, add 4 to that. Still a 4/3 x here. Add the 4 to this. Remember, 4 is the same thing as 12/3. So I'm going to be adding 12/3 to this. That gives me a total of 4/3. That is my equation. And if you want to get a little bit more satisfaction out of doing all that work, come back here, grab your calculator, tell your calculator to graph that curve. Second, go back to the y equals, because most of you do have some kind of a TI calculator. Graph the second equation. What you should see is a curve from this one, and a line from this one, and this one is going to be the tangent to the first one. A bunch of work. You might want to try this 2 times until you get the system down. It's a nice problem to work with. It looks terribly complicated to begin with, but using the chain rule, it makes almost child's play out of it. Not quite really. Let's be real. There's the curve, there's the line. That's what you should see on your calculator, and that should feel really good. You can see the tangent here. You can see the curve here. Everything comes together. Nice. Some simplification techniques. So find the derivative of that. That looks a little bit complicated. It's too bad that square isn't inside the square root. That would make things a little bit easier, right? However, there's the original function. Rewrite it using the fractional exponent. Now here's where you have to be real careful. What you got up here is the function is a product. So the first thing you do is use the product rule. The first function times the derivative of the second one, plus, because you got the product rule, then you reverse the roles. Take the second one and the derivative times the derivative of the first one. Take the actual derivatives with the power rule, and just be real careful. Simplify, factor, simplify. Put the answer back in radical form, because this 1/2 power means square root, and the minus means pull that thing down in the denominator. So the x stays on top where you'd expect it. This one has an exponent of 1. It stays on the top. This one goes on the bottom, and because the 1/2, it gets the square root on it. And you've got a nice answer. Next, find the derivative of f of x. We've got a function inside a function, and that inside function is a quotient. So we're going to be combining several things. This is a lot of practice, and this also tests in a way whether you've got the product rule and the quotient rule down. Just take them one at a time. So, for example, we'll use this as y, and here's our 3x minus 1 over x squared plus 3. Make that look like a 1, and that's squared. So this one is the inside function, So if I want to take the derivative, I'm going to bring that 2 out front, leave what is inside alone, 3x minus 1, oops, over x squared plus 3. The 2 minus 1 becomes a 1. Good so far. And the chain rule says, just use the general power rule. That's what we just did. When you do that, then you want to take the derivative of what's inside. The 3x minus 1 over the x squared plus 3. You're going to take the derivative of this one. This is the 1 over here. This means derivative. So what do we have so far? Our derivative. Here's our 2. If we look at this first part here, we've got 2 times the 3x minus 1 over x squared plus 3. On the second one, we've got a quotient. Now I know it looks scary, but remember, you can do this all by itself, and that's all you have to do, one step at a time. How does the quotient rule work? The quotient rule says take that denominator, x squared plus 3 times the derivative of the top. And because it's a quotient rule, we have minus here. Then we'll reverse the roles. We'll have x squared plus 3. We'll take the derivative of that this time. And then we'll leave the 3x minus 1 alone. On the bottom, we have the square of the denominator. So x squared plus 3 now gets squared. There's your derivative. A little bit of work to do here. Our derivative is, so we'll leave this first part alone for the time being and keep our fingers crossed that maybe something works out to make this a little bit simpler. Just copy that nicely. Okay, now what do we have here? Well, I've got some derivatives I have to take. So I'll just leave this x squared plus 3 for now. The derivative of the 3x minus 1, hey, this isn't too bad. There's a 3 minus. We're going to take the derivative of the first one. That's 2x. Hey, maybe Mr. Sailor's not nuts. This is okay as long as I take it one step at a time. Alright, not too bad. See what we've got now. The derivative of the whole thing, and what do I have? We'll copy the first part again. We've still got our fingers crossed that this gets a little bit simpler. On the top, I'm going to be multiplying 3 times the x squared plus 3. So 3x squared plus 9. Now over here, I'm going to be multiplying negative 2x times the 3x minus 1. So negative 2x times 3x is negative 6x squared. And then negative 2x times negative 1 is a plus 2x. And keep that x squared plus 3 squared in the bottom. Okay, let's see what we've got. We've still got the 2 and 3x minus 1 on the top. and we've still got the x squared plus 3 on the bottom. What do we have over here on the right? Well, we've got 3x squared minus 6x squared. That's a minus 3x squared. And I've got a 2x plus 9 over x squared plus 3 squared. Okay, let's see. I don't see any way of factoring. It would have been nice if this part on the top was factorable. I don't really see anything. So what's my final derivative? All right. So I've got 2. I've got 3x minus 1. I've got minus 3x squared plus 2x plus 9. And on the bottom, I've got x squared plus 3 squared. Not elegant, but we're done. That's it. Okay, next. So that's what we did. Notice we brought that 2 that had been here. We brought it out front. Reduced the 2 to a 1. Then we took the derivative of that quotient, which gave us that, and that, and that. That's the best we can do. Next, an application. Of course, this is business calculus, right? Or calculus for social sciences. So I'm not sure if these are actual figures or not. It doesn't matter. We need to play with something to get accustomed to using the chain rule. Our model is going to be good from 2004 to 2013. We already had an example on the test that we just had in a previous video about how you can create these models. So perhaps someone took the numbers, the sales numbers from 2004 to 2013, and they found that this is a good model. Remember, the sales figures came from 2004 to 2013, so if we let T represent the number of years after 2000, our model is good for 4 to 13, or 2004 to 2013. Now, what do we want to do? It says use the model to approximate the rates of change in those 3 years. And would Apple stockholders have been satisfied? Now, what does that mean? Well, if you were a stockholder, what would make you feel good about Apple stock? If the stock is rising, right? That means if you sell it, you make some money. So what are we going to do? We're going to take the rate of change of S by taking the derivative of that. We look back here, well, notice right here, here's our S. Another way of putting that is it's the sales figures as a function of T. We want the rate of change for 3 of those years. So we'll take the derivative of s, and notice what we have here is a function inside a function. So if we would take the derivative of that, we'll bring that 2 out front, because square is the outside function. Bring 2 out front, and don't touch what's inside. 0.035 t squared minus 0.134 t plus 1.19. So you treat the first part without changing anything that's inside. Once you've taken the derivative of the outside function, 2 out front, 1 up here. Now you take the derivative of what's inside. The derivative of the first part, take the 2 out front, 0.07, t squared becomes a t. The derivative of the middle one just becomes negative 0.134, and the derivative of the constant is a 0, and there's your derivative. There we go. Oops, I missed a number there, didn't I? Yeah. We'll fix that. Now what they did also was they multiplied the 2 times what's inside the parentheses. So 2 times the first one, 2 times the second one, 2 times the last one, and there's your derivative. So to find out what's happening in 2006, just put a 6 in where the t is, and you get 95 cents per year. Now what does that mean? That means the stock is going up at 95 cents every year in the year 2006. So as a stockholder, you're thinking, oh good, the stock is going up, it's gaining in value. Fantastic. How about 2009? Just put a 9 in where you put the 6 in before. It's doing even better. It's going up at $2.81 per year. 2012, just put a 12 in and see what you get. There's a graph of those sales. That's the original function. You can see that the stock is increasing in value faster and faster. That's even better. Last of all, a review of some of those differentiation rules. You have all the rules you need. All we're going to do is work on applications most of the way for the rest of the semester. You've got the power rule, you've got the product rule, the quotient rule, the chain rule. You've got a lot of power, excuse the pun. Here's what we've had so far. The first one is the easy one. If you've got a constant, the derivative is 0. If you've got a constant in front of it, take the derivative of this function right here, and just leave the c out front and take the derivative of this part of it. Sum and difference rules, self-explanatory. That's something you probably would do without even thinking about it. Product rule, remember, each one of those functions gets multiplied times the derivative of the other function. And put a plus because this is the product rule. Quotient will do somewhat a similar thing, except because the quotient rule, you'll have a minus, and also the function that was in the bottom gets squared. Two things about the quotient rule to remember. It's different from the product rule. The power rule is just the chain rule on steroids, I guess. Bring that n out the front, reduce the n by 1. Chain rule, you get an inside function and an outside function. Outside function, inside function. Just bring that n out front, reduce the n by 1, take the derivative of the inside function. Here's one way of looking at it. And you are really ready to differentiate almost anything. I'm going to show you some interesting things on the way, how to optimize a bunch of other things. You've got the basic rules that you need to do a lot of work in calculus. Well, congratulations, you made it a long way, and you're ready to do some real calculus. Take care and differentiate carefully.